Okay, so now we are getting ready for the second talk of the morning. Kanae and Tsushima is going to talk about type debugging and collaboration with Glück.
Yes. Yes, thank you very much for introduction. Good morning, everyone. Today I'd like to talk about type debugging using partial evaluation. And usually it's a work that uses type of partial evaluation aims to get first evaluation, but this work is just for use partial evaluation or is very useful for program understanding. Yes. And sorry, I forgot to say, introduce myself. I'm Kanae Tsushima, and this is joint work with Glück. Yes. And first, I'd like to start from the motivation of our work. If you have experience to write a scale or organ code, then I think you might face the same problem. Compliance type error message are not insufficient for users in many cases. So for example, if we consider this kind of real-type token program, then this is the error message from compiler. And this says the function part is very complicated, but it will ultimately result in print string. So the type of function part is string to unit. And the function is applied to 1, so of course it is type error. But if the user cannot understand what is the return value, then it's because the function part is very complicated, so it's difficult to understand the error message. Because our error message says this one is type int, but it's expected to type string. So for solving this kind of programs, so complicated the expression makes very hard to understand the cause of type errors like this. And for that we are inspired by Hazel, that is a structure editor that can run incomplete and ill-typed programs. So for the previous example, the Hazel can produce this kind of result, so print string 1. Then user can easily understand, oh, this function part is print string, so of course we need to fix that part or well, because they are conflicting. But for that, Hazel also introducing the special evaluation rules for real-type programs. But if we'd like to have this kind of evaluation for random languages, it is a bit difficult to implement. It will be a heavy burden. So our question is, are there any other way to evaluate real-type programs? And our answer is we'd like to use partial evaluation for this purpose. And actually, our work is not alone using partial evaluation for program understanding. And there is another work by Buzzy and Perform for program understandings. And they focus on well-typed programs, and we focus on ill-typed programs. Yes. And as for that, so for obtaining the partially evaluated result, we use these 3 phases. We assume we will use the input, +2 plus 2 and false. This program is of course real-typed because the second argument of this expression is Boolean, but it is applied to plus is applied, and plus is the type of plus is into it. And for partial evaluation, we need to annotate something. So this red bar means annotation, and this red bar means dynamic in partial evaluation. And that dynamic means it cannot be evaluated in the partial evaluation phase. And of course, we'd like to get more evaluated results. So first we increase the closure parts, And then next we decrease the prices. Then finally we can use partial evaluation. And I would like to see the result. We would like to see what is happened in the running example. Yes. And we pass the original type program to compile type inferencer. Then compile type inferencer said this part is the source of the type error. This is type error. Then in increasing phase, we make the located part dynamic and this frozen part. Then we pass this problem again. Then compile type inferencer said this is real type. So we know this red part is enough to make the whole program real type. Sorry, I forgot to say this the type of red part will be ignored. So this program will be well typed. Then next is decreasing phase. We'd like to decrease the number of frozen parts. And for example, we are considering all elements of this red part. Then we are considering from left to right. So first we try to unfreeze this through, and then we pass this expression to combined type inferencer. Then it combined type inferencer says this is working. So we know we can unfreeze this through. And like that, similar to this, and also can be unfreeze, and also is also possible to unfreeze. And for this hand, the program will be passed to compile type inferencer, and compile type inferencer says this program is type error. So we know this hand cannot be unfrozen. And then next, finally, this is a last expression, and this is well typed. So we know this black part can be evaluated. Then in partial evaluation phase, we pass this annotated program to partial evaluation. Then in this case, there is a true and false. That expression is evaluated to false using partial evaluation. And for this partial evaluation phase, we just use a state-part online partial evaluator because that is enough to use. And of course, you might already know, false and false should be evaluated to false. So for treating such problems, we introduce another strategy. The simple strategy means the previous strategy I taught, and the improved strategy is a bit improved. And hopefully, the strategy of simple of freeze increasing phase is just freezing only located paths by type error messages. Yes. So in that case, true and false, only that part will be located. So we just freeze that part only. And but improved strategy, we freeze more paths. So if when we will use type of inference, there is a bias from left to right, but that's not good to treat each expression fairly. So we will freeze all expressions in that function irrigation. And in the simple strategy of decreasing phase, we just unfreeze each part from left to right. But each expression should have some preferences. So we decrease in improved strategy, we decrease frozen part with some preference using some heuristics. So for example, in this program, we unfreeze only because if we can evaluate the second argument, it's very nice. So we first complete the second argument, then we try the other things, then this class will be remained to be free frozen. So, yeah. And for evaluation, we introduce new criteria for the debugging approaches. Yeah. And first one is burden on the users. Also, if we would like to comparing other works, we need to check this point. And the second one is the use of locating the source of type errors. And actually, this criterion is a bit difficult to check, so we just check these two things. First one is the ill-typed programs fully evaluated. Of course, if we pass the ill-typed programs, but the system returns the same program, it's not useful. So it should be evaluated as much as possible. And for the second, so to be the type conflict visible in the result is also important things, because if the user cannot understand the type conflict using that seeing that result, that's not bad. That is not good. So we checked these two things. Yes, this is a result of improved strategies, and we use the test cases. And yeah, the test cases are coming from two sources, and one is a student program, and another is online implementation of hyperaccelerator sculpture. And the test cases are very simple real-time programs. And we tried 15 examples, and the second one means the result of improved strategy. And the third one means it's fully evaluated. It's just checking the result is whether the result contains unevaluated, how can I say so? It's possible to evaluate, but it's not possible. It's not evaluated. And the fourth one means it's type of evaluated result, because if there is not if it is not fully evaluated, we have to compare the size.
How big are these programs?
It's not so big, so it's maybe at most it's 6 lines or something like that. Yeah, so it's a very small typical cases of type errors. Yes, and for improvement strategy, we try to check the three criteria, and because our system does not require users' interactions, so there is no users pattern. And everything is fully evaluated, so if we see the result of improved, there is nothing that can be evaluated. For example, if you might consider this can be evaluated, but in on-camera class is the type of class should be int to int to int, so we can evaluate this without So that part is not very typed. And to be, can we see the type conflict? It's an important thing, and most so for example, we'd like to see the result, and almost the results are mixed color, so black and red. In that case, we'd like to see the result like this. This is an example of real-time expression, and this is evaluated to 3 plus empty list. And of course, just looking this 3 plus empty list, the user can see, oh, there is a type conflict between class and the empty list. Yes, and so if that is mixed colors, then just evaluated result is enough to see type conflict. And other cases are this one. So test 3 and 5, 6 and 15 is just the black color. So just looking this, we cannot see type conflict. And for that case, yeah, this is an example of that case because yeah, there is a pattern matching over list, and if the list is empty list, it returns empty list. And if it is not an empty list, it returns integer. So there is a type conflict like that. And for this program, our implementation returns 2. Because, yeah, 1 plus 1 will be 2. And from this, yeah, of course, if we only see these 2, we cannot see type conflicts. So our system returns also the annotated program like this. Then the user can see there is a type conflict. And actually, if the user's intended result is this 2, then the place that should be located is this red part. So user need to fix this red part. So yeah, this is not partially evaluated, but this information is very useful to locate the source. Yes, and this is a different strategies result. And many cases are similar to the improved strategy. So this is just different result from improved strategy. And our system do not require any input by users, so there is no user's burden. And with the criterion 2A, test 1, 3, 4 are not fully evaluated, unfortunately. So for example, we can see plus 3, 3 can be evaluated to 6, and plus 1 can be evaluated to 2. And for test case, test 4, it's the closed part is a function part. So the partial evaluator cannot evaluate anything at all. And for taking the criterion to be, we can see type conflict because there is better black colors. And from the comparison of these 2 results, we know it is important to have a good strategy to have a good result. Yes, let me conclude my talk. We introduced a new way of type debugging, and please note that we are not saying our approach is the best type debugging approach. So we just introduce a new way for type debugging. So user can choose good one for their purpose. And for that, we enabled partial evaluation of real-type programs, and the idea is freezing parts of programs using the type of inferencer, and we simplified using by partial evaluation. And the difference of majority bug using partial evaluation is we just throw away the partially evaluated result after user start debugging. So we do not focus on the first evaluation. And the things we'd like to do next is, of course, we'd like to improve the strategies by using more examples. Because currently, the example I showed, improve, say, result is very good. But of course, if we try other examples, it might be not fully evaluated result. So we'd like to improve that strategy. And second part is that we'd like to track after the user understands the conflict. For example, in the example that the beginning is a complicated function and one application function of that is evaluated to print string 1. And after that, of course, all user understand there is a conflict, then they try to fix that one. But the user can see only the evaluated result and it's a bit far from the original program. So they cannot, they might be take time to fix the original one, the bug in the original code. So we'd like to see such kind of trace. So for that, maybe program stepper might be useful, but of course, program stepper always receive well typed program, so it might be needs to consider. And the last thing is extension of the language. Currently, we treated very basic syntax of vocabulary, and for the program, for evaluating programs of novices, that's enough. But of course, if I believe our approach might be useful for professionals, so for that we need to extend the language, our languages. And that way, of course, we need to treat higher order functions and exceptions. And about this exception is a problem because partial evaluation and exception are not treating exceptions in using partial evaluation is a bit difficult program because partial evaluation might change the order of evaluation. So yeah, for that part, we need to consider about how to handle exceptions. Also, there is a related bug, so we'd like to consider about such kind of things. Yes, that's all from my side. So thank you very much for listening.
Thank you. Questions? Question over here.
Thanks for the talk. I think the motivation is clear and good, but I don't still get how the proposed solution is connected to the motivation. So for example, in your example of whatever, 1 plus 2 and 4 samples or whatever, I think the type checker already gives an error message pointing that the second argument is a boolean, not an integer, and I can get how the result of partial evaluation helps the debugging. So could you give me kind of intuitive explanation from the user perspective?
This kind.
Yeah, I have this example. So how this output, last line, help user debug this program compared to just type checker output?
Yes. For this, for actually the improved result is different from this. So 2 plus false might be the result. And the user can understand, there is a type conflict between plus and false. And of course, this false is evaluated result. So we need some way to present this in this. So you are right. So we need some way to trace so that there is a user can understand the top type conflict in this work, but user need some way to fix this information or fix this bug in the original program. So the second future work is related to that.
Thank you.
Yeah, I think you had this tracking problem on the last slide.
Exactly.
But it's not easy, I guess, to track in the right way.
Yes, exactly. So, sorry. And so the thing, our work is focused on to see off.
Are we
So
getting
sorry,
to talk
I
in
think,
Japanese
yeah.
as well?
Sorry. Yeah, so this one is very related to his question.
So this question.
So the thing, yeah, it's still ongoing. So our work is just to understand the type conflicts between in that program. And after that, we need to track something. So if we receive print string 1, then, oh, we'd like to fix print string path, then we need something to understand, yeah, we need to show some tracking of that part. So the result is print string, and the user need to fix print string, then fetch where this print string come from. Yeah, that's a problem.
How long does it take to execute your debugger on the largest programs you have?
Yeah, it might be take time because our approach does not do any efficient, yeah, things, so it might be long.
What have you seen in practice when you did your experiments?
In my experiment, it's not so late, but it user might wait a bit. Yes. Thank you very much.
Other questions?
So do you
Oh,
plan?
you can.
So do you plan to have any user study and as actual students whether the improved messages actually help?
Yes, I'd like to do that, and it's a bit difficult to consider, but yeah, I'd like to do that. I think that is very important to have actual experience.
Very good. Any last questions? Thank you very much.
Thank you very much.